Let's continue our discussion in matrix algebra and talk about matrix multiplication. There are two types of matrix multiplication: scalar multiplication and multiplication by another matrix. Scalar multiplication is when you multiply a matrix by some constant we'll call k. K is called a scalar. The new matrix k times A is the same size as A, with each entry of A have been multiplied by k. So let's go ahead and let A be this matrix shown, and we'll let k, our constant, be the number 4. We will find the scalar multiple of A, Ka, or 4 times A. When we multiply 4 times the matrix A, we are multiplying each entry of A by the numbers 4. So 4 times 3 is 12. 4 times 5 gave us 20, etc. The matrix 12, negative 16, 20, negative 4 is the scalar multiple of A. In other words, we multiplied A by the number 4. We scaled it up by 4. Here are some facts about scalar multiplication. For these facts, let's go ahead and let K and H represent any scalars. So like the number 4 and 7, or negative 1 and 3. So just any constants, or they could even be decimals or fractions. And we'll let A and B be any two matrices. So we use capital letters often to denote matrices. Then we can say that scalar multiplication is commutative. So K times A is the same as A times K. Order in which you multiply a scalar by a matrix doesn't matter. Secondly, scalar multiplication is associative. So if we have K times H times A, we can group H and A together and then multiply by K, or we could group K and H together and then multiply by the matrix A. And finally, scalar multiples can be distributed. So if I have the sum of two matrices A and B, I can distribute K to be multiplied by both A and B. So K times A plus K times B is the same thing as adding A and B together first and then multiplying by K. Now let's talk about matrix multiplication, when we decide to take one matrix and multiply by another matrix. To do that, we need to define what a row vector and column vector are. A row vector is a 1 by n matrix. So that means it has one row and n columns. Let R1, R2, R3, all these little r's represent the entries of our row vector. You can see that there are n r's in one row. A column vector is similar, but it is an n by 1 matrix. Our column vector C has, again, n entries, C1, C2, etc., all the way till we get to Cn, but it has n rows and only one column. The product of a row vector and a column vector is a number, or a 1 by 1 matrix. So if I multiply R times C together, I am taking my row vector R, which is a 1 by n matrix, and multiplying it by my column vector C, which is a n by 1 matrix. And to do that, I'm going to take each corresponding entry. So R1 times C1 plus R2 times C2, right? This one times this one, plus this one times this one, until we get to Rn times Cn. And that result is a 1 by 1 matrix, which contains a single digit. So it really is just a number. It's worth noting that, again, the number of rows in our row vector is 1, with n columns, and our column vector has n rows with 1 column. Notice that the number of columns in our row vector matches the number of rows in our column vector. These n's are equal. And then the number of rows in our row vector is 1, and the number of columns in our column vector is 1. And so a 1 by 1 is what we ended up with. Let's do an example where we multiply a row vector by a column vector. My row vector is 1, 2, 3. My column vector is 4, 5, 6. First, note that my row vector is a 1 by 3 matrix, and my column vector is a 3 by 1 matrix. The number of columns in my row vector matches the number of rows in my column vector. Those 3's match. And then the number of rows in my row vector matches the number of columns in my column vector, which results in a 1-by-1 matrix. So here's the work. We're going to take 1 times 4 plus 2 times 5 plus 3 times 6. And if we calculate all those products, we get 4, 10, and 18, which add together to become 32. So I could write this 32 as a 1-by-1 matrix, but leaving it as this whole number is just fine. So let's expand this idea to multiplying not just row and column vectors, but any arbitrary matrix A times another arbitrary matrix B. So we've talked about the compatibility of their sizes. So notice that matrix A here is an M by R matrix and B is an R by N matrix. Our goal here is going to be to get the product of A and B. So first we have to check off that when multiplying matrix A by matrix B, the columns of A, so that's this R value here, must equal the number of rows in B. So that's this R value here. So let's write them next to each other. So the columns of A must equal the rows in B. So these two must be equal. So that's good. Secondly, we'll realize that the size of the product matrix AB will be the number of rows in A times the number of columns in B. So the size of our product here is going to be an M by N matrix. So let's go ahead and do an example. Let's let matrix A be this 3-by-2 matrix, and matrix B will be this 2-by-3 matrix. So if we want to find the product of A and B, are they compatible? So in other words, do they have the right size? So matrix A has 2 columns and matrix B has 2 rows. So since these two numbers are the same, then we know we can do this multiplication. Second, we'll notice the size of the matrix is going to be a 3-by-3 matrix. So when we multiply these two matrices together, we'll go ahead and give ourselves an open matrix that's a 3-by-3. So we have 9 different entries that we're going to have to find to fill up this 3-by-3 matrix. Each entry corresponds to a row from A and a column from B, because we're taking a row vector and multiplying by a column vector. So starting with our first entry here, row 1, column 1, our x11 entry. So that's going to be the first row of A multiplied by the first column of B. Really understanding the indices of each of these entries is helpful because it reminds you, okay, row 1 from A and column 1 from B. The 1, 1, row, column. It's always row, column. So row 1 from A is the 1 and the negative 1, and column 1 from B is 2 and 3. So our row vector times our column vector means we're multiplying 1 times 2 plus negative 1 times 3, which gives us 2 plus negative 3, which is negative 1. So we'll enter our 1, 1 entry as negative 1. Now our x21, 1, 2 entry is, again, first row, second column. First row, second column. We're going to take the first row of A and multiply by the second column of B. So 1, negative 1, and 8, 6. 1 times 8 plus negative 1 times 6 equals 2. So this entry becomes a 2. Our next entry is going to be the first row, third column. So our x13 entry will be the first row from A, the third column from B, and when I do that work, 1 times negative 1 plus negative 1 times 0, I get a negative 1 to put in this position. Now moving on to our second row, we're going to look at the entry x21, so second row of A, first column of B, gives us 0. Our x22 position is going to be the second row of A and the second column of B, which gives us negative 12. Our x23 position, second row of A, third column of B, gives us 3. Our x31 position, third row, first column, third row of A, first column of B, is 15. Our x3, 2 position is going to be our third row of A, second column of B. That results in 30. And finally, the very last position, x3, 3, third row of A, third column of B. That's 0, 5, negative 1, and 0. When I multiply 0 times negative 1 and add it to 5 times 0, I get 0. And so this is my answer to the product of A and B. So what if we take those same matrices and we multiply them in the opposite order? So instead of A times B, what does B times A look like? So first, let's make sure they're compatible. We have a 2 by 3 on the left and a 3 by 2 on the right. Because the number of columns in A matches the number of rows in, well, I should say the number of columns in B matches the number of rows in A, they are compatible. And the resulting size of this matrix is going to be a 2 by 2. So we don't have 9 spaces to fill up here. We only have 4 spaces to fill up here in this 2 by 2 matrix. So again, identifying the indices, our x11 position is the first row of A multiplied by the first column of B, which produces -2. Our second entry here, first row, second column, first row of A, second column of B. So 2 times -1 plus 8 times 2 plus -1 times 5 gives us 9. So we can fill out our entries for the first row now. Now our second row is going to be our x21 position. Second row of this first matrix here, which is B, I think I said A earlier, multiplied by the first column of this matrix, which is A. Second row, first column gives us -15. And our last entry, the x22 position here, is going to be the second row of B and the second column of A, which gives us a 9. So our answer to the product of B times A is the 2 by 2 matrix, which has 4 entries, -22, 9, -15, 9. That's our answer. So what did we learn from that exercise? When we multiplied A times B, it was a 3 by 3 matrix, and B times A was a 2 by 2 matrix, and they were not the same. So B times A is not equal to A times B. That means that matrix multiplication is not commutative. The next question I'll ask you is, what is the matrix multiplicative identity? In other words, if I have any matrix, we'll just say A, B, C, D, what matrix can I multiply it by in order to get this matrix back out? In other words, the matrix that doesn't do anything upon multiplication. The multiplicative identity is the matrix with 1s on the diagonal and 0s above and below. This matrix should look pretty familiar. I've drawn a 3 by 3 identity, but just know that the identity can be any size as long as it's a square. That's how you get the 1s on the diagonal and 0s above and 0s below. So here's an example. I have this matrix 0, 5, 6, 9, 4, 2. It's a 2 by 3 matrix, which means in order for me to multiply it by an identity matrix, I have to use the I3 identity matrix, because I need the number of rows in this matrix to be 3, because the number of columns in this matrix is 3, right? I need these to be equal. A 2 by 2 wouldn't work here. The result of the product of these two matrices is going to be a 2 by 3 matrix, and we know it should, because if this really is the identity matrix, we want to be able to take this matrix, multiply it, and get the same thing back out. So let's go through a couple entries. So this x11 entry is going to be a 0, first row, first column. This second entry here is going to be first row, second column. And that gives us 0 times 0 plus 5 times 1 plus 6 times 0. And so you see how the zeros are strategically placed, and the 1 is strategically placed to leave the digit in the position that it's supposed to be. So we get this 5 here. What should we get here? We should get a 6, right? So first row, third column gives us, again, see how the 1 is only positioned to be multiplied by that last digit? And if you kept going with this process, you would see that the second row results the same, 9, 4, 2. So that's how the identity matrix works. Let's go ahead and change our definition, though, over here to represent any arbitrary size, any matrix IN, where n is the number of rows and the number of columns in the matrix. So we have, this arbitrary size, 1s on the diagonal, 0s everywhere else. So what would the I2 matrix look like? It's a 2 by 2, so it would just have 1, 0, 0, 1. We did the I3, this is I3. How about I4? What does I4 look like? 4 rows, 4 columns. So we have 1, 0, 0, 0 for the first row. Then we'll have 0, 1, 0, 0 for the second row, 0, 0, 1, 0, 0, 0, 0, 1 for the last row.